Okay, let's unpack this. We talk constantly about progress, building, growth. But the reality is we exist within finite planetary boundaries, and there's this inherent tension there, right? How do we get the progress we need for everyone to flourish without, well, consuming the very future we're trying to build?
That tension is, that's the defining professional challenge of our time. So our mission today is to really dive deep into what it means to design a thriving future, but without using up the future itself. And for professionals like engineers and geoscientists, this isn't some optional feel-good thing. This framework, it defines their core obligation to the public interest and, crucially, to environmental stewardship in every single project.
Right. And in the material we've synthesized for you, it actually provides a surprisingly clear structure for this massive balancing act. It defines the boundaries we can't cross, the ethical duties, and even the practical tools we need.
And we're going to go beyond just, defining terms. We'll be looking at concepts like planetary boundaries, the ethics of intergenerational equity, and the practical side of things like the circular economy. We'll focus on the friction, the challenges of moving these ideas from a blueprint into the real world.
So if we're going to talk about a finite world, we have to start with this concept of limits. What are they exactly? Are we talking about philosophical ideas or hard physical boundaries?
Oh, we're talking about hard physical boundaries. Absolutely.
Yeah.
When we say limits, we mean the natural, the physical, the ecological thresholds of the planet. These are points of no return. If you cross them, human activities can cause irreversible damage.
So we're talking about eating into the principle, not just using the interest.
That's a perfect way to put it, yes.
And we see these limits making headlines every day, don't we? They're incredibly concrete.
They are. Think about running out of non-renewable resources, like certain minerals we need for all our tech, or the ecosystem's limited capacity to just absorb our waste. The atmosphere can only take so much carbon dioxide before the warming becomes, well, catastrophic. Then you've got constraints on fresh water, on soil fertility. These aren't just inventory problems, they're structural.
That is a powerful distinction, because recognizing limits means you have to accept that unlimited exponential growth, the kind our modern economy is built on. It's just fundamentally unsustainable inside a closed system.
It is. It has to be. And that recognition leads you right to the core concept of sustainability. If the limit is the hard wall we can't hit, then sustainability is the instruction manual for how to maneuver inside that wall.
And what's the best definition we have for that manual?
The foundational one, the one professionals really rely on, comes from the 1987 Brundtland Report. It defines sustainability as development that meets the needs of the present without compromising the ability of future generations to meet their own needs. It's really a moral imperative.
Okay, so how do you actually execute on that? The sources talk about 3 interconnected pillars, and I think this is where people get tripped up. They only think of the first one.
Right. The first one is environmental sustainability, protecting ecosystems, air, water, soil. That's the obvious one.
The one everyone knows. But then you have economic sustainability,
which is about promoting long-term prosperity. I mean, a project that just depletes resources or creates massive environmental costs for someone else to clean up, that's not economically sustainable in the long run.
And the third pillar, and this is the one that seems to cause the most friction, is social sustainability.
It really is. This means ensuring equity, health, safety, community well-being. So you could build a bridge with, say, recycled steel and zero-emission concrete. Sounds great, right? Environmentally and economically sound. But if putting it there destroys a community or poisons the local air, it fails the sustainability test completely.
So ignoring any one of those pillars means you're basically failing your professional duty.
Precisely.
Okay, so to measure that success across all 3 pillars, professionals have these frameworks. Let's talk about the triple bottom line, or TBL.
Right, the TBL. It's a way to make sure we're looking at more than just a financial spreadsheet.
So it's people, which is social equity, planet, environmental responsibility, and profit economic viability. But let me introduce some friction here. Doesn't this sometimes let a company just, maximize profit while doing the bare minimum on the other 2, kind of using the framework as a shield instead of a compass?
That is the daily challenge.
Yeah.
It absolutely is. The key insight here isn't just balancing them, but seeing that a lot of traditional profit metrics are in direct conflict with planet longevity. So the professional's job is to mediate that conflict, to advocate for systems where your economic viability actually comes from your environmental efficiency, not at its expense.
Okay, an example.
Prioritizing long-term energy savings over a cheaper but less efficient installation up front. That's a classic one.
Got it. Now, moving from the balance sheet to the planet itself, what's fascinating is how science has actually quantified some of these hard limits we talked about, this idea of planetary boundaries.
Yes, this is huge. Environmental scientists have identified 9 key global processes, things like climate change, ocean acidification, freshwater use, that regulate the stability of the entire Earth system. For a professional, the most important thing is knowing which of those boundaries their work is likely to affect.
So, which ones are engineers and geoscientists most often pushing up against, maybe without even realizing it?
Well, land system change is a big one. Converting forests for agriculture or cities, that hammers biodiversity. But a more insidious one is the flow of nitrogen and phosphorus, what we call biogeochemical loading. This often comes from agricultural runoff or sewage, and it creates these vast dead zones in the ocean. When a geoscientist advises on land use, they are directly mediating whether we cross that boundary.
So, if the planetary boundaries are the danger zones, then the UN Sustainable Development Goals, the SDGs, they're like the global blueprint for action, the positive roadmap.
That's a great way to think about it. The SDGs give us specific targets, which in turn create market signals. And for engineering and geoscience, a few are really critical. Goal 7, clean energy. Goal 9, infrastructure. Goal 12, responsible consumption and production. And of course, Goal 13, climate action. Aligning your project with these is fast becoming a standard expectation.
But wait, responsible consumption, goal 12. Doesn't that seem like a complete non-starter for clients whose whole business is built on selling a lot of stuff? How do professionals handle that pushback?
They handle it by focusing on optimization and lifespan. It's an innovation challenge. If a professional can design a product that lasts 3 times longer, the client has, in theory, met their Goal 12 compliance by selling one-third the material over the same time. That's where the R&D budget goes, proving that long-term value creation can outperform short-term volume.
Let's get into the specific roles then. Engineers are positioned as the primary innovators here because their designs literally determine how resources get used and what emissions are created.
Every single choice, the material selected, the system specified, it all dictates resource use. And the key tool they have to compare these choices is life cycle analysis, or LCA.
An LCA is so much more than just kicking a box. It's looking at a project from cradle to grave. From the moment you dig the raw material out of the ground all the way to construction, operation, and what you do with it at the end.
That's right. So an engineer might be deciding between, say, structural concrete and mass timber. LCA calculates the total embodied carbon, the energy used to transport it, the potential for recycling, the waste from construction. It's like comprehensive environmental accounting. It lets them pick the option with the lowest overall impact, not just the lowest initial price.
And on the other side of that coin, you have geoscientists. They're the stewards, providing the scientific understanding that says whether a project is even feasible in the first place.
Exactly. Geoscientists are the experts in resource limits and renewal rates. They calculate sustainable yields. And not just for mining, but for things like groundwater. They're the ones monitoring aquifer depletion and telling a city, look, the water you're using today takes 1,000 years to naturally recharge.
And they're also vital for hazard mitigation, right? Making sure we don't build something that a future climate event is just going to wipe out.
Absolutely. They track environmental change, advise on responsible land use. Their work informs the decisions that balance what we need with what the planet can handle.
So if I'm an engineer, just out of school, how does knowing I'm responsible for something as huge sounding as intergenerational equity change my day-to-day decision on whether to use material A or material B? It sounds overwhelming.
It's a mindset shift. It really is. It requires you to shift from just solving the immediate design problem to optimizing the long-term system. So instead of asking, is this structure safe and affordable today? The ethical question is, will the energy demands and the waste from this structure compromise the well-being of the community 50 years from now? It forces you to prioritize things like resilience and recyclability over just the immediate cost.
Which leads us perfectly into the practical tools. Let's talk about 2 huge shifts: resource efficiency and pollution prevention.
Resource efficiency is just the mantra of doing more with less. It can be simple, like robust recycling programs, or really complex, like using AI to optimize a manufacturing line to minimize scrap material, getting more output from less input.
And pollution prevention is a vital mindset shift away from, the end-of-pipe solution?
Exactly. Instead of just putting a filter on the smokestack to catch pollution after you've made it, you focus on cleaning up the process itself. You change the design so it doesn't create the pollution in the first place. If you stop using a toxic solvent in your process, you don't need a massive, expensive system to treat that toxic waste later. You've saved money and eliminated the risk at the source.
And this ties right into the circular economy, where that old take, make, dispose model gets thrown out entirely.
The circular economy requires us to see waste as a resource that's just been misplaced. You have to design products specifically so they can be taken apart, reused, and remanufactured. It's a huge effort to close the material loops, to stop needing new virgin resources. It takes radical collaboration between designers, material scientists, everyone.
And here's where it gets really interesting. We're seeing a boom in innovations that make the circular future actually possible. Things like green materials. The big push for low-carbon concrete and recycled steel is drastically reducing the carbon footprint of our infrastructure.
And we can't forget the digital tools. Advanced modeling, AI, GIS. We can now model climate impacts with incredible detail and optimize these solutions in real time. You can predict the performance of a sustainable design before a single shovel ever hits the dirt.
And we can see this happening in real-world examples. Canada, for instance, has had some big successes integrating these principles.
Oh, absolutely. Think about the massive Hydro-Quebec Clean Power Network. It's a colossal engineering project that has to manage resources and the environment carefully, but it provides clean power to millions. That project wasn't just about profit. It had to deal with huge land system changes, biodiversity, local community impacts, linking back to all three of those pillars.
That's a perfect example of the social pillar being key. It's not just about the tech.
It's never just the tech. Or look at Vancouver's Greenest City Action Plan. That mandated sustainable infrastructure at a city level. Professionals had to apply these principles to entire systems: waste management, energy, transportation.
And even in tough sectors like mining, we're seeing this innovation. Research into reducing waste, reclaiming land faster, protecting biodiversity. It shows that even resource extraction can be done more responsibly. These examples prove that these ethical frameworks can be translated into large-scale reality.
But ultimately, all these technical tools, they rely on a foundational ethical commitment. It's rooted in professional codes of conduct. The mandate is always to hold paramount the safety, health, and welfare of the public, and the protection of the environment.
And that duty is formalized by that concept we touched on earlier, intergenerational equity. It's the obligation to make sure that our progress today doesn't steal opportunities from those who come after us.
Professional conduct also demands absolute transparency and honesty. That means accurately communicating environmental risks. It means not greenwashing.
Yeah.
Greenwashing, pretending a product is more sustainable than it is, isn't just bad PR. It's a professional breach of integrity. It destroys trust.
And it's not enough to just follow the rules, is it? Professionals are expected to show advocacy and leadership, to actively champion these practices, even when short-term profits seem to point in the other direction.
And that's where the real challenges lie. Overcoming that economic pressure is often the biggest hurdle. Sustainable options can have higher upfront costs, so you're forced to advocate for a long-term investment over a cheap, immediate fix.
Another huge one is just uncertainty. These environmental systems are so complex, you can't predict everything. This is where the precautionary principle comes in, right?
Yes, it means you have to act responsibly and minimize risk, even when you don't know the full range of consequences. Better safe than sorry, basically. And finally, it all demands continuous learning. The science evolves, new materials are invented, professionals have to keep up. And we need massive global collaboration to share what works across different countries and industries.
So, to bring this whole deep dive back together, the takeaway seems pretty clear. Limits define the boundaries we can't cross. Sustainability gives us the ethical framework to work within those boundaries. And professionals have to use tools like life cycle analysis and the circular economy to safeguard the future through this idea of intergenerational equity.
And what's really fascinating is that this duty, it goes way beyond just delivering a project on time and on budget. By understanding and respecting these planetary boundaries, professionals aren't just safeguarding natural systems, they're safeguarding the very structural stability of civilization itself. It is, I think, the ultimate measure of professional integrity.
That's a powerful thought to end on. Thank you so much for joining us on this deep dive into professional responsibility in a finite world. If you found this discussion valuable, please like and subscribe. It really helps and ensures you don't miss future discussions that turn complex information into crucial knowledge.
Until next time.